Okay, so in 7.2 we covered overall reactions like substitutions, eliminations, additions. Those show overall processes, but what's happening along the way? How can we break it down into the individual steps? Sometimes reactions will go just in one step, but often there are several steps involved. And when we go to that level of detail, how each bond breaks and forms, that's when we're starting to look at reaction mechanisms. So if we have something with multiple steps, we'll see intermediates formed, but even in a single step process, assuming the product is different from the starting material, which has to be the case for any chemical change, we have to see some bonds broken and some bonds formed if we're talking about organic compounds. So there are two main types of overall reaction, and in a concerted reaction, everything happens in one step. So with a concerted reaction, you have to make all the new bonds at the same time as you break all the old bonds that are going to end up gone. However, many processes are, so that's concerted, many are stepwise, and in those there are multiple steps. We have multiple steps going along the way to the product. And so this would be a simple case like A plus B gives C all in one step. This would be something like A plus B gives X, and then X and a separate step decomposes to the product, let's say C. The most powerful way to show a mechanism is to actually show how each bond is formed and each bond breaks. And remember, a bond is made up of a pair of electrons, so if we show the flow of electrons, we can show how those bond changes occur. So we usually use red. That became traditional. I believe Jim Hendrickson always used red chalk, my PhD advisor, and so he put that in the textbook when he wrote his part of the Hendrickson-Kremenham textbook. It shows these curved arrows. Now this is a very powerful way, and you can use it to see if a mechanism makes sense, because if the arrows are going the wrong way, if you have arrows going towards an electron-rich center, then your mechanisms are probably flawed. Or if you're going to end up with too many electrons or too few electrons, that will become very obvious once you start doing this arrow pushing, as it's called, or sometimes pushing electrons, things like that. So there are various rules for how you should do this, and I'll cover those next. Okay, the most basic of these rules for arrow pushing is just that these curved arrows mean movement of electrons, not atoms. And I know I've more or less defined it as this, and yet very often students will show arrows to mean atoms jumping around. Try and leave the atoms where they are, and move the electrons between them to show the change in the connections. So it makes sense that electrons are going to flow from electron-rich centers towards electron-poor centers. So always make sure when you're looking at your mechanism that you're, where the arrows start is a nucleophilic center, and where they end up is electrophilic. Now, thinking about where those arrows go, what happens at the start of the arrow and the end of the arrow is always going to be the same. So think about the start of an arrow represents a pair of electrons moving away. Now, you might think that if you have an atom and a pair of electrons moves away from it, somehow it would go 2+. But in fact, what happens usually is if you have, say, a lone pair to begin with, and that pair of electrons moves, it forms a new bond. And when it's forming a new bond, it's gone from having 2 electrons all to itself to having 2 electrons shared. So the net result is actually a +1 increase in charge, because it's still sharing the 2 electrons, it's just now they're shared between 2 atoms instead of being all on one. Alternatively, you can have a bond breaking where you have a shared pair, and when that bond breaks, the atom that's left without will also go +1 in charge, because it was sharing a pair before, and now it's not got anything. So, in summary, what we do is where the arrow starts, that's what will happen. And what happens at the other end? Well, as you can imagine, what happens at the other end is more or less the opposite of this. We're going to form a new lone pair or bond, and the charge on the atom is going to go -1. Tail. Okay, so our bond has been broken here, or the lone pair is gone, and then we form a lone pair or bond. The only other rule is that you can kind of see this if the starting atom goes +1 and the ending atom goes -1. The other atoms in between should stay the same. And certainly overall the charge will stay the same. Because at least in chemistry, you can't create electrons out of nothing. So you have the same number of electrons at the end as you had at the start. All they're doing is moving around. Okay, so let's look at a few examples now. Okay, so we'll look at some simple examples now of these mechanisms. And I'm going to start by being a bit cheeky and doing it wrong, because this is something I'm sure I will see on next week's test from many of you. I'm sorry to say that, but please make sure it's not you. So what a lot of students will want to do is go like this. Because they say, okay, this hydrogen was attached here, and it's now going to attach over here. So we kind of want to move the hydrogen over like this, and Well, this bond is a pair of electrons, so that's kind of a flow of electrons, isn't it? But unfortunately that's wrong, because we have to show the flow of electrons we are going to break this bond, but if you look, the pair of electrons has to go onto here, not onto here. If we move, once we remember this is a pair of electrons that's moving and not the atom, we would realize this atom would, this nitrogen would go 1 minus, and this chlorine would go 1 plus, because that's the direction of the arrow. And you can see it's the other way around. This is actually a good leaving group, so it actually wants to form Cl minus. This lone pair goes towards the electrophilic hydrogen and kicks out Cl minus. Breaking that bond, a pair of electrons ends up on chlorine, so it ends up 1 minus. Now, I just have another example to show you that mechanisms can show quite complicated processes, and just to scare you a little bit, this is a mechanism we'll see next semester. I'm going to draw in this hydrogen so you can just see what's happening here. Now, if you follow down the chain, you can see where the arrows start. This atom goes from being neutral, being 1 plus. Where the arrows end, the atom goes from being neutral to being 1 minus. And I just broke my own rules, because if you look, this overall is neutral, this overall is 1 plus, so that's telling me I've got to put plus on there. And you can see each arrow here, a lone pair is lost. We make a new bond where it ends up. Here we break a bond, make a bond, break a bond, make a bond, break a bond, make a lone pair, all the way down the chain. So these cascades are quite common, and in fact there's a beautiful mechanism of how steroids are synthesized in your body, where there's about 10 electrons all go ding, 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 and make about 4 rings all in one step. So these cascades can happen fairly easily. But what we want to do next is look at elementary steps, which are the individual steps that can be added together to make an overall reaction scheme. So we can summarize every overall mechanism in terms of a combination of elementary steps. So we'll look at that next.